Here we go. Today, I don't even think I have all that much to say today, but today is day 4 for AAHL 1. We're going to be going over 2.3 on IB, which is features of graphs. And when I heard that, I was like, okay, cool, we're gonna have to go through some but honestly, we're not. We're just gonna go through basic old features of graphs straight out of Algebra 1. Of course, you're gonna have to know how they really work and see some more complicated graphs, but we're gonna start by talking about x-intercepts and y-intercepts. I hope you'll forgive me for not writing out intercepts, but I don't want to spend forever today. The x-intercepts and the y-intercepts, I hope you can define these and feel very confident that the x-intercept is where f of x crosses the x-intercept, the x-axis, and of course the y-intercept is pretty much the same thing. Where f of x, crosses the y-axis, and what is that? Sure, we gotta know that. How mathematically could we solve for those two things if we did have an actual function? Sure, we're looking at a graph, that's very easy, but what if we have a function? Also should be a pretty easy answer. What you got? Plug what in?
Plug x for 0, plug y for 0.
There we go, right. We need to plug in, and what we're looking at is those 0 values. On the x-axis, this is all the place where y equals 3, y equals 2, y equals 1, but right here, this is all the place where y is equal to 0. And so if, for our x-intercept, we want to find it, we need to set y equals 0. That's something you definitely have to have on lock. You have to know that to find that x-intercept, you need to set y equals 0. A lot of times that's where we have to set y equals 0 and then factor and set all of our factors equal to 0 and all that kind of mess. Our y-intercept is wherever the f of x crosses the y-axis, and that's where we set x equal to 0. And typically this is the easiest one because when you plug in a bunch of zeros for x, everything just typically starts to fall apart, especially for polynomials and stuff. The y-intercept is very nice, very easy. There's not really much else to talk about for this stuff, right? I mean, it's a y-intercept, it's an x-intercept, you plug it in. I do, again, going straight to Algebra 1, going straight to Algebra 2. X-intercept is one of those things that has a lot of different names you might hear on a quiz or on a homework or something like that. What are some other things you might hear? Roots, very good. Roots. What else?
Zeros.
Yep, zeros, and there's one more really.
Oh, I don't know that.
Yeah, so domain has to do with x values, but it is not the x-intercept. Those are not, they're in the same realm, but they're definitely not synonyms. These are all synonyms, so if it says find a solution, you're looking for all those things. Your calculator is extremely strong, and part of the reason, I'm sure you've heard people be like, oh my god, Desmos teachers, oh I hate Desmos. Desmos is too good for the kids, right? The problem is, a lot of algebra just says, tell me the solution, and solution is the same thing as x-intercept. So anybody can type it in, look for the x-intercepts, and oh, there's all of our solutions. So that's why do we have 4 words that all mean the same thing? Because we're doing algebra, and sometimes we're looking at graphs, so x-intercepts looks great. Sometimes we're working with factors, and so roots looks pretty good. Sometimes we're solving algebra equations, so solutions works good. So it just all kind of depends on the lens that you're looking at these questions. But this stuff, it's easy, sweet. We know how to do this, x-intercept, y-intercept. We're not scared by that. We have maximums and minimums. what is a maximum?
Highest point.
Yeah, I mean, you can keep it pretty simple, and you can say the highest point. Maybe that's a little too simple, but it's generally right. If you go with the highest point, you're pretty much gonna get it right. It is the largest, or the highest, I don't really like the word highest as much, but the largest y value on a, I guess we could say domain, maybe that's a little bit better. The largest y value on a domain. And the domain is just like a range or a set. The reason that we can't maybe just say the highest value is because maybe we have a function that looks, all kinds of crazy stuff, and there's many maximums here. There's some, you might remember, local maximum or relative maximums and absolute maximums, hopefully words you've heard before. It's the largest y value on a domain. So a lot of times in this class, they'll say, here's your function, there is your domain to work with. What is the maximum within this region, within this domain, within this locale? So, of course, a minimum, it's almost a waste of time to write it out, but you guys get it. The largest, smallest, I guess. Smallest y value on a domain. And these are somewhat formal definitions, informal definitions, but I think they're doing good enough. I think you guys understand minimums and maximums. Do we feel like we need a better definition of these things? Okay, now, how can we solve algebraically for the maximum or the minimum? Up here, it's just set y equals 0, that's easy. Set x equals 0, that's easy. Let's say I give you this function, y equals 2x squared minus 5x plus 1. If you want, where it crosses the x-axis, set y equal to 0, boom, and try to solve it. You might have to use the quadratic formula for this question. Or the second one, where the y-intercept is set x equals 0, that's easy, the value's 1. But how can we find the maximum of this graph, just algebraically? The truth is, we don't really have a lot of tools for that, okay? That is a large part of calculus and what calculus is and why you learn calculus. And so this maximum and minimum stuff is not very algebra heavy because you guys just don't have the really, you need calculus to know how to do the maximums and the minimums. And so we'll revisit that, I suppose, next year when we get to calculus. In the meantime, you still might have to find maximums, but it'll be, you're looking at a table, or you're looking at a graph, or you're allowed to use your calculator, and so you have to do some calculations, and we'll talk about that today. As far as these things go, it's pretty self-explanatory. Max, min. 2 more. Go, go, go. We have the domain and the range. Hopefully we know one of them's x and one of them's y. Which one's which? The domain is x. Let's see, I'm sure you had it. You're absolutely right. The domain is x and the range is y. Do we have any fun ways to remember that? The reality is, just remember it. It's not all that hard. The way I like to do it is, you say x and y, you never say y first, you never say y and x. Same with domain and range. You've never heard anybody say range and domain. It just doesn't quite work the same. So you say x and y, domain and range, so your x is your domain. I don't think you need any kind of fancier reason than that. Now, your domain is basically all of the x values where your function exists. All x values where f of x exists. In algebra, a lot of times it's like, okay, cool, the domain is all row numbers because the line goes everywhere. And then you get another graph that looks like this. and the domain is still all real numbers. Boring. And then you get another graph, and it looks like this, and the domain is still all real numbers. Do you guys know any types of graphs that do not have all real number domains? Exponential looks like this, and that is a very good attempt, but that does also have domain all real numbers.
Isn't it logarithmic?
Yeah, so logarithmics and exponential are basically inverses of each other, and the log graph looks like this, and so the domain does not exist over there, less than 0.
Square root.
Square roots is another good one. Your square roots look like this. Also, any of those really crazy rational graphs or reciprocal graphs, have you guys seen these ones that look like that? Right, the boomerang graphs, I don't know, we have some silly names for them in Algebra 1, but those type of graphs have these asymptotes, hopefully a word you've heard before, and wherever you have asymptotes, your domain does not exist there, your x values do not exist there. So we will be working with harder examples and harder graphs, and so the days of the domain pretty much always being all real numbers are behind us. And the range, I hope you've already written it, are of course all y values where f of x exists. Oh. All right, D6. We glad we got D6. You have a question?
Like domain notation. Because there are 2 types.
Domain notation, you said? So domain notation, if that's a good point here. Notation. If you have a graph and you have a domain, and let's just say our graph looks like this, and it's not going to be all real numbers. It's going to be from -6 to 5. We need to set up a domain. A lot of times we'll put a big D domain. And then we need to go from -6, that's our small number, to +5, that's our biggest number. And so I'll put -6 and I'll put +5. Now, one way we could do this is with inequalities. And so we could put an X in the middle and just think about that like all of our X's are in the middle of these two terms, these two numbers. And then we need some inequalities, and they always go this direction. Because these are the small numbers where it's less than, and these are the big numbers where it's greater than. So that is one way to do it, like inequality notation. We do have a slight issue with this graphs domain. Anybody pick up on the problem that I had?
Less than or equal to.
Yes, we should have less than or equal to, and a lot of the time you're gonna have those less than or equal to's. If you have something like an asymptote, you can't put the equal to because you can't be equal to it. The range, we're gonna need more numbers on our graphs because these are x values and they don't really matter for our range. Let's just say we have -2 and +6 or something. We could also do something interval notation. Have we ever seen interval notation? That's with either parentheses or brackets. Talking about parentheses or brackets. Which one of these includes or has equal to for it?
Brackets.
The brackets, right? So that's these ones, nice job. That one does not. And so for this graph, it's very similar. You just put the small one, you put the big one. We don't need the y in the middle this time. Comma will do. And because we have solid points and solid points, brackets and brackets. Two pretty solid ways. There's also set notation. I want to get to the problems, but we won't worry about set notation just yet. Does that kind of help you out? Answer the questions?
That's where like the rules like the blue line X is therefore.
That's the set notation. I think we're good today. We'll talk about that Wednesday or Friday. This is 2 pieces of paper. And we're going to look at this stuff together.
The thing didn't work. It didn't work.
Oh, okay. I appreciate you also on the office staff.
This one is great, but it's just don't open.
Are you going on the rightmost door?
The,
The one right next to the buzzer?
yes.
Okay. I believe you 100%. I definitely believe you. Second problem. Can I get these up on? We'll try it real quick. Import PDF. Teaching HL1, Unit 1. This is day 4. Cross your fingers. Oh my god, best teacher ever. It's insane. Alright. Here we go. What do we think about this? Does this scare us? Or are we doing okay? We've got a graph here. I wasn't very creative when I came up with my example a second ago because it looks almost the same as this one looks. We have some different values we can find. They're probably hard to see on the video, but maybe we'll do a zoom in or something. Write down the domain of the function. Let's in white still. Here we go. Black. Okay. Anybody got the domain of this function for me? 211. Do we want to use interval notation? Do we want to use? Let's do intervals. Sure. We can do bracket 2, 11 bracket. Okay. Write down the range of the function be, what do you think? 2, 6, right? Again, now we're looking at the y value, so it's 2 and it's 6. That's where our function exists. Does it exist at 1? No. Does it exist at 7? No. So we're going with 2, 6. Brackets, brackets. Write down the minimum and maximum value of the function. We've got the whole picture of the function right here. There's nothing going off screen, and so we just need to find the minimum and the maximum value. And just like we have in the notes, those are going to be the y values. So what would you say is the, up first it says minimum. What would you say is the minimum value?
92.
So a good question, do we need the x value that goes with the y? This just says, tell me the minimum value. So as far as I'm concerned, we could just say the minimum is equal to 2. That's good enough. If it said find the location where you have a minimum, okay, now we want to incorporate that x value, and it is at 9, nice job, but this is good enough. And the maximum is equal to 6. Of course, look at the range, 2 to 6, the minimum, the maximum, not too bad. What do you got?
So since the 6 doesn't have it's not like a vertice, like would it still like count? Because like I thought maximum was like when they like connect. Like
So would you choose this instead?
yes.
But what about, do you not want to count this vertice?
No, because it doesn't have like it stops right there. There's no arrows, or it doesn't like continue.
If that was the case, is it 5, wouldn't 5.5 count?
Because it's not going down, so it's not like a point.
So you're saying it's gotta be increasing and then decreasing afterwards. I think 6 is our maximum y value for sure.
Can you explain why?
Imagine this is our money, how much money we made every day this week. And I said, what is the maximum amount of money we made every day, like this week? I don't think you would say like, well, you can't count 6 because it didn't go down the next day, right? You'd just be like, oh, 6 is the most we sold. I think that.
So on a cubic, when it has the arrows, that arrow counts as the maximum?
Like this, if I say find the maximum of this function here, and I'm just saying find the maximum value, infinity, that's what I would say, going on forever. Now, most of the time they'd say, okay, find the maximum of this function. It's like, okay, now we're looking for this, or find the maximum between -5 and 5. Okay, we're looking for that, or find the local maximum or the relative maximums. but this is just asking, especially because it has a solid point, it's just asking for the maximum point, and 6 is the biggest number, so I'm going with 6. We can look at the key after this, but I'm feeling confident. Complete the table of values. What do we think about this? The x value is 2, we should be 3, yep, and then 4 is right here, where should it be at 4, and then 6 is right here, we should be at 5. What values are we choosing for these? Well, 2, there's only one option because it's down here. 2 has to be at the x value of 9. This is bringing in kind of what Lexi was saying, the x value that goes along with the minimum. And then 6 has to be the value at 11. Now we could have gotten to a bind, right? What if this question asked us, what is the x value at 3? The reason this is a different kind of question is because the y value at 3, right here, happens multiple times. It happens early, happens in the middle, it happens late. And so if the question looked like this, it would have multiple answers. So good news, it doesn't look like that. Otherwise, we'd probably be scratching our head thinking, which one does Mr. Collier want? So, nice job. D, okay, we did that. E, given f of x equals 4, there are 3 possible values for x. Nice, look at how good that was. Exactly what I was just talking about. We did D up above, so this is gonna be E. Did we get the 3 possible values for 4? 4, 7, 10. Easy, right? Feeling good? Sweet, flip it over. Do we have a calculator?
Good afternoon, because
afternoon.
of staff, it is that time when you have the opportunity to release students to come back and get their electronic devices that they were taken earlier today. So if you could allow them to come to the office at this time, we appreciate it. Have a great night.
Oh, much better. Okay, do we have a calculator? If we don't have calculators, we have options over here. Who needs a calculator? Raise your hand. 1, 2, 3, 4. You're welcome. Okay, do you need one as well? All right. We don't have a Okay, on Friday, I will have a form to let you 4 rent a calculator if you don't have one. Of course, that means you can't lose it. You'll be responsible for it. Okay? All right, number 9. Find the range for the following functions given the domain. Well, we get these functions, and this can be an exhaustive process. Find the range means find all the different y values. Does it go up? Does it go down? And this will take a very, very long time to do explicitly by hand. You have to plug in a bunch of numbers, and who even knows? The good news is it says with GDC, a graphic display calculator. How can we type this function into the calculator? Y equals, and so let's get that in there. 2x squared minus 8x plus 9. Part of why we're doing this together is I want to make sure you know how to do all of these calculations and stuff using the calculator. We can see the graph by pressing the graph button. So I'll press graph. When I press graph, no surprise, this is a nice quadratic function, and yeah, I press graph and it looks like a nice quadratic function. I know there's nothing really funky going on here. It says find the range, which is the y values. I don't really have to worry about it going back down like this because that's not how quadratics work. If you ever get nervous, you can go to table by doing second graph and maybe looking up, looking down. It's like, yeah, okay, this graph is just going up forever, no stress. Now, we need to find the range, which means how high does it go up and how far does it go down? What is the highest y value that we get to? Infinity. Certainly it's going to be infinity. Looks like they've been using these inequality notation, so let's use the same thing. Inequality. It's never going to be an equal to equality because we're never going to quite reach infinity. The problem for this one, however, is the lower bound. What is this smallest value? We got any answers? 1. So we can go to table, second table, and we can scroll around maybe and look for our lowest value. I see 9, 3, 1, 3, 9. It definitely looks like it's around that value. We do want to be a little careful and just make sure. Now, this is so symmetrical that it makes it kind of obvious that's what the answer is going to be. But what if it was a little bit of an uglier kind of table? We didn't quite know if we could trust. We could, you said the y-intercepts?
I mean, for like this.
But we don't know that the y-intercept is really all that important when it happens to this, right? I mean, if the graph's over here, the y-intercept's going to change and it's going to be different. We can use our calculator to calculate the minimum values. Do we know how to calculate the minimum values of a graph? Okay, so using our calculator, there's the graph button on the far right. There is the table button on the far right. And next to that, there is the trace button. And what does the trace button do? It lets you trace along the graph. Kind of boring. I don't know why we would really need this, but it does let us trace the values. But second trace is very important because second trace allows you to calculate. And this is where the calculator can do many, many things. We have the option to calculate the value, to calculate the 0, which we can translate to x-intercept. We can calculate the minimum, the maximum, the intersect. All of those things incredibly valuable. If the question says GDC and you allow this, you have an insane calculator, computer of possibilities here in your hand. So if we want to calculate the minimum, that's number 3, we can press enter. Now, I'm not sure how to get this bigger on the screen, so I'll just kind of describe to you what you got. What you got is this picture here on your graph. You've got a couple of blah, blah, blah up there at the top. Then at the bottom, you've got x equals blah, 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 and y equals blah, blah, blah. But right here, it says left bound. And what that means is basically make a left boundary for your graph. So I'm gonna make a little bit more room by just moving the whole thing here. What we need to do is put our cursor anywhere on the left side of where we'd like to look. So if you can see the little spider on your curve, you can press the left or right arrow key. You have to make sure that this minimum that we're targeting, you press enter when your line is on the left side of it. Once you press enter, it will say right bound. Cool. So now you gotta take your little spider on the line and go over, enter, and make sure he's somewhere on the right side of the minimum. The next one says guess, which is kind of a waste of time. Guessed is helpful if your curve has a lot of ups and downs and you want to make sure it targets a specific one. But for this case, we can just guess whatever we want. We can just press enter. We don't really have to guess at all. And then it will tell you almost exactly what that value is. Now it says here 2.000002. Calculator's almost too smart for its own good. But the y value is what we want. And just like Devin predicted, he's exactly right. It's 1. So our thing here would be 1 less than or equal to x less than or equal to infinity. Oh, we're doing the range. Did I have x on here earlier or y? If I put X, that's a big mistake, big goof. And now, before we move on just a bit more, whenever you're doing these, the infinity sign that you have there is also kind of a waste of time, because if we get rid of the infinity, this means the exact same thing, that y has to be greater than 1. There's no reason to put the infinity on there at all. So, a lot of times people will rewrite this so that the y is first, y is greater than or equal to 1. Okay, we've overdone this question, we've talked too much about it. Now it says find the range for the following functions given the domain. So, this time we want to check from 0 to 2. 2 is where we just found our lowest value. One thing you can do on your calculator is change the window. Do you guys know about the window button? If you press the window button, you can change what your graph shows, kind of like Desmos, how you can scroll around. So when it says from 0 to 2, if you press window, you can change that from 0 for the x minimum to 2 for the x maximum. And now when you press graph again, it's only going to show you that graph from 0 to 2. And when you do that and you look at the graph, I guess it doesn't even show the graph quite like that, but looks like this. And that makes it really obvious. Okay, our graph is always going down here. Our graph has no funky ups and downs. It's just a straight up down, which means this is going to be our maximum and this is going to be our minimum. Those are values at 0 and at 2, and we can go to the table to grab those good enough. We don't need to do any fancy calculating maximums and stuff like that. So I would say that the value at 0 is 9. These are ranges, so we need y's. Oh, I got to do it backwards. Struggling here. The 9's the big number, and 2 is 1, our minimum, of course. We do the same thing for the next range from 0 to 5. If you want to change it, you're welcome to. The x minimum of 0, the x maximum of 5. You can check out the graph. This time you see it does go a little bit up and down. We can check out our table from 0 to 5. Because it includes 5, looks like 5 is going all the way up to 19, so we kind of have a new winner here. Our minimum is 1. And our maximum is 19. And the last one says, find the range when x is less than 0. So this time, we're looking on the other side. Again, if you want to keep changing your window to get the better picture you can set the minimum as like -10, the maximum is 0. And now you're looking at a picture that is just this side of it. Anybody got an idea what they'd go for the range of this one? Y greater than or equal to 9. Okay with that? Okay. Using this calculator, do we feel okay about calculating minimums, calculating maximums, maybe changing the window to look around a little bit? What if you get really nervous because your calculator is just all messed up and your zoom looks terrible and you're zoomed in on a really weird place and your graph isn't shown up there because the graph's not in the middle anymore? How can you reset the zoom or reset your whole calculator? Do we remember? If you want to reset the whole thing, second plus 712 will give you a full reset. And that can be nice because you know everything's fresh. You do have to be a little bit nervous about your radians and degrees if we're doing some trig stuff, because it's going to reset that into radians. A lot of times that messes up trig kids. But second plus 7, 1, 2 will reset everything. It'll reset your table. It'll reset your zoom. There's also zoom 6, the zoom button right in the middle by the graph. If you press zoom, 6 is zoom standard. So you can press zoom 6 and it'll take you right back to the normal graph. It's kind of like when you hit the home button in Desmos, and it just brings you back to the middle. That's also what zoom 6 does. Anyways, all just calculator things and calculator tricks. The next one is find the range for the following functions. They are giving us the picture. We can use these maximums and minimums, calculating. But did everybody feel okay about like the left, right, guess type feature? Make sure if you're looking for the maximum that you hit calculate maximum. Or if you're looking for the minimum, you hit calculate minimum. These are asking for different ranges, so we definitely want to use Y values. Again, I like to use table a lot when I'm going through these and figuring these out. We're kind of running out of time here, but let's look at this last page. On this last page, it's not gonna sharpen up at all for me. It asks us to sketch the graph, indicate the roots of the equation, to write down the maximum value, and to write down the range. We get this crazy function, 2 minus x squared minus e to the power of x. Does everybody feel confident that they can type that in the calculator? 2 minus x squared minus... Where's the E button on the calculator? Do we know? Second divide. Have we ever seen the E before? It's a number E, cool. It's on second divide. So second E power x. We can hit graph. We can look at the graph. Nice. Doesn't really look like we need to zoom around too much. So they asked us to sketch it. Okay, there you go. It does say indicate the roots of the equation, where f of x equals 0, of course, where y equals 0, which is where our roots are. If we go to table, we could look for any place where the 0 shows up, but it doesn't. And that means that these roots are happening at decimals, weird decimals. We could solve this equation for 0, which sounds like a nightmare, or we have the calculator. So how can we calculate the roots here? We can do second calculate 0. Now, when we go to do this, we want to think about there being 2 different roots. And so when we do left, right, guess, make sure you're zoned in on just one root. If you make it more like this, the calculator has like 2 options to go for, and you're not going to be able to find kind of both of them. So one at a time, we'll do left, right, guess. Move your little spider to the left, enter. Move your little spider to the right, enter. And then when it says guess, who cares? You can just press enter again. What I got for this value right here would be the x value of negative 1.31. Doesn't really say how many decimals. We'll do 3 decimals. 5, which rounds up to 6. And then comma, the y value equals 0. So there's the 1 root. And we can do second calculate 0.
Good afternoon,
Left.
teachers, staff,
Good
and students.
afternoon.
It's wonderful
Right.
Wednesday, also
Enter.
known as Home Day, and it is time to know.
All right. Why don't we say finish the rest of what we didn't do on this? We did a decent amount. If you worked harder than me, maybe you're already finished. If you don't have a calculator, can I trust you for one day? Take my calculator home. Can get one to like do for homework already. Okay, Trey. If you don't need it, you don't need it. You can give it back to me, and that will avoid you losing it. But if you do need it for this homework, you can take it home today. But don't look. And if that's good, you guys are good to go.